that I do not forget. Okay, so now it's recording. And yeah, whenever you want to start, I can present you and we go.
All right, we'll wait till 5 past, I guess.
Mm. Yeah.
Mm-hmm.
Oh, you're right, 05. All right, so welcome everyone to the Pure Math seminar of UNSW Sydney. And today we have the pleasure to have Colin Reid from University of Newcastle, and he's going to talk about groups acting on trees with prescribed local action. All right.
Thanks, Arno, and thanks for the invitation to speak. Okay, so I'm going to start with some background on why we were doing what we're doing, then our main theorem, and then a few applications. So, so about half this talk will just be background. So, okay, so start with the basics. So for us, a graph is a set of vertices and a set of arcs. Each arc has an origin and a terminus, which could be the same. So we have maps O and T from the arcs to the vertices, and each arc has a reverse arc. And I'll just note that we differ from Serre in that we allow an arc to be its own reverse. If it's a loop, it could be its own reverse, or it might not be its own reverse. We allow both. And aside from that last point, you can also think of graphs as a kind of metric space where the vertices are some discrete set of points, and then for each arc, each pair of an arc and its reverse, you glue a real unit interval to the endpoints of the arc. So I'm just saying that so that I can say things like simply connected and so on, and it makes sense. So for instance, here is a graph. We allow loops, multiple edges. And then a tree is a graph that doesn't have any loops or multiple edges, and it's connected. So here's a tree. Which another way of saying that is that there's a unique path without backtracking between any two vertices. Okay, so given a graph, an automorphism is a permutation of the set of vertices and arcs that sends vertices to vertices, arcs to arcs, and respects the origin, terminus, and edge reversal. And we equip the automorphism group with the permutation topology. So this is the topology in which the stabilizer of any vertex or arc is declared to be open, and you take the topology generated by that. So the basic open sets here are the stabilizers of finite sets of vertices and arcs. So some special cases of this topology: if the graph is countable, then aut gamma is a Polish group, which means it's separable and completely metrizable. So this is a nice class of topological groups. The class that I'm most interested in of topological groups are totally disconnected, locally compact groups. And we get one of those if the graph is locally finite. So that means that every vertex has finitely many, sorry, that should say, yeah, it's locally finite and connected. So locally finite means that every vertex has finitely many arcs going into it or coming out of it. And in some sense, you can see well, you can't exactly see all totally disconnected locally compact groups this way, but you can understand the general theory of totally disconnected locally compact groups just by thinking of automorphism groups of connected locally finite graphs. So there's sort of the connection sort of goes both ways there. Then when we take subgroups of Aut gamma, we just give them the subspace topology. Okay, so we have a nice setup here for talking about topological groups, or a certain family of topological groups. The relationship between trees and graphs is that trees are the universal covers of graph theory. So if you have a connected graph, then there's a tree that maps onto it in a locally bijective way. So if you look at a single vertex and the arcs coming out of that vertex, that lifts to the tree, where you have the vertex in the tree and then all the arcs coming out of that vertex bijectively. But obviously a single vertex of the graph can have lots of pre-images in the tree. So usually the covering tree will be infinite even if the original graph is finite. So here's an example. The colors are just to indicate how the covering works. So we've started with a graph here with 3 vertices, and we produce a tree such that it's the neighborhood of each vertex. The arcs coming out of each vertex look like they do in the original graph. So if we have a blue vertex here, it should have 1 red neighbor and 1 green neighbor. And then if you have a green vertex here, which should have 2 red neighbors and 1 blue neighbor, and so on. And you build out a tree, and you can see this is going to be an infinite tree. And that's the universal cover of this graph. Now, this kind of universal cover idea also applies to groups acting on graphs. So given a group acting on a graph, you can lift it to another group acting on a tree. And in general, this will be a much bigger group with an associated homomorphism that's locally surjective, in the sense that if you take a point stabilizer of the group a vertex stabilizer of the group acting on the tree, and then map it to this group acting on the graph, it will give you the vertex stabilizer of the group acting on the graph. This isn't enough to specify what fires uniquely, but there's a standard way of doing this. So the point I'm getting at here is that if you understand groups acting on trees, that actually tells you something about groups acting on all graphs via this sort of universal cover idea. And maybe, in particular, sorry?
Just a little question. Yeah. Can you give like a easy example of to get like a G tilde from like a easy group?
Yeah, how does it go? Yeah, I'm trying to think of one off the top of my head. I mean, basically the kernel of tilde is the sort of group that has trivial local action everywhere, and I'm about to get onto local action. So there's sort of a kernel of the local action. So
Or even for a very small group, huh? Like Z over NZ or something like that.
Yeah, like if you had if you had, say, like a triangle, then the automorphism group of that is what is it? D6, I guess. So that lifts up to so the universal cover of that is a line, and you have a copy of the infinite dihedral group acting on the line, but it's acting with sort of 3 orbits of vertices. And sort of at each vertex, you can flip the, so that would be an example,
Okay, thank you.
So in particular, if we have, even if you're just interested in finite graphs, it's useful to be able to think about actions on infinite trees as a way of sort of going to the simply connected world. So for instance, there's a problem in finite graph theory called the Weiss conjecture about automorphism groups of, originally asked about finite graphs, but you can rephrase it as a question about automorphism groups of trees. This is something my colleague Stéphane Tournier is working on. From a group theory perspective, there are 2 fundamental constructions that give rise to actions on trees, which are free products with amalgamation and HNN extensions. And if you don't know what these are, don't worry. It's not going to be important for the rest of the talk, but these are basically sort of they're some of the most basic ingredients for producing new groups by sticking groups together. The standard approach to construct and describe this process is called Serre theory. So I'll just give a very brief idea of what Serre theory does. Given a group acting on a tree without edge inversions, then the action can be described by a graph of groups. So you have a graph which represents the quotient of the action of G on T. So that means the vertices and arcs correspond to orbits of vertices and arcs of the tree. And then for each vertex of gamma, you have a vertex group, which corresponds to the vertex stabilizer in the tree. For each arc, you have an edge group, which corresponds to the arc stabilizer in the tree. And if you stabilize an arc, then you also stabilize its reverse. So we make the edge groups the same for an arc and its reverse. And then we have a specified embedding of the edge group into the vertex group for each end of the arc. Because of course the arc stabilizer is a subgroup of the vertex stabilizer. If you fix an arc, you also fix its endpoints. And conversely, given a graph of groups, you can construct a group acting on a tree that has that graph of groups, which is called the fundamental group of the graph of groups. This has a certain presentation, which I don't want to spell out, but there's a standard construction you do starting from a graph of groups to produce a group acting on a tree. Okay, so this looks like we've got a pretty good handle on groups acting on trees. And the downside is that once you get down to vertex and edge stabilizers, you're not really doing Serre theory anymore. Serre theory isn't so useful for a group that actually fixes a vertex or fixes an edge. In particular, the vertex stabilizers could be more or less anything. So every countable residually finite group or every countably based profinite group has an action, and usually many different actions, on a locally finite tree where it fixes exactly one vertex. So Serre theory works great if you understand what the vertex and edge stabilizers are, or if you know that they're small, but it has its limitations if you're not assuming that you know everything about the vertex and edge stabilizers. So for some applications, what we'd rather do is take local actions. So given a graph gamma, group acting on gamma, and a vertex of gamma, we say the local action at the vertex is the image of the vertex stabilizer in the group acting just on the arc coming out of that vertex. So we don't look at the vertex stabilizer acting on the whole graph, we only look at how it acts on the arcs immediately incident with this vertex. Similar to the Serre setup, we only really need to think of orbits of vertices. So we can consider the local action at GV to be the same as the local action at V, since the vertex stabilizers are conjugate, and obviously the conjugation sends the arcs incident with one vertex to the arcs incident with the other vertex. So this is less information than knowing all of the vertex stabilizer. But one reason this is a natural thing to do is if you take a graph and then pass to its covering tree, then the canonical sort of G tilde corresponding to your group G, the vertex stabilizer will get much bigger because you're acting on this whole tree instead of the original graph. But the local actions are the same because the cover has sort of preserved the neighborhood of a vertex. So local actions are really the kind of structure that gets preserved by this universal cover approach. If we know the local actions of a group acting on a tree, we don't know everything, but we can sort of pin down what we do know. So here's a definition from Banks, Elder, Willis, although the idea is older. So if you have a group acting on a tree, then so we define the IP1 closure of G by saying we're going to put an automorphism of the tree in GIP1 if for every vertex of the tree there is some element of G such that H inverse G fixes every element of O inverse V. So in other words, we say that H is an element of the IP1 closure if for every vertex there's some element of G that acts the same on the neighbors of that vertex, on the arcs coming out of that vertex, right? But it could be different vertices, you could choose different elements of G. It's a fact that this is always a group. If you start with a group, you take its IP1 closure, you get another group. And then we say that G has property IP1 if it's equal to its IP1 closure. So Banks already showed that when G is closed in Aut T, then this is equivalent to an older condition called P, which was introduced by Tits in 1970. So I haven't written the definition of P here, but basically the idea is that you take a path in your tree, which could be finite or infinite, and then that if you take the sort of closest point projection of the tree onto the path, that defines a partition of the vertices into these sort of subtrees. And you want the pointwise stabilizer of this path to act sort of independently on each subtree. So it's sort of the direct product of the groups acting on the subtrees. So that's how Ted's defined it. But the Banks, Elder, Willis definition is sort of more convenient in terms of local actions. And they turn out to be equivalent once you've got a closed subgroup of Aut T. So what's interesting about Tits property P is that you can use it to produce examples of simple groups. So if you have a group acting on a tree with property P, and we also assume it doesn't fix any ends of the tree. So an end is like an equivalence class of infinite forward paths, where you say two such paths are equivalent if they sort of eventually coincide. So suppose that G doesn't fix any end of the tree, and it also doesn't preserve any subtrees. So sort of some geometric density assumption there. And then you take the subgroup G plus, which is generated by the arc stabilizers in G. Then what it shows is that every non-trivial subgroup of G that's normalized by G plus contains G plus. So in particular, G plus is trivial or simple. So for example, if you take a regular tree, let's say a regular tree of some finite degree D, then its automorphism group doesn't fix any subtree or ends, but the group generated by the arc stabilizers does preserve the bipartition of the vertices. So there's this natural bipartition of the vertices of a tree where every vertex only has neighbours in the other part of the partition. And Aut T plus preserves that. And that actually turns out to characterize Aut T plus in that case. So it's you get a simple subgroup of index 2 in the automorphism group of a regular tree. Okay, so so from now on, we're going to stick to closed subgroups of Aut T to avoid technicalities, and refer to property P and the P closure. So I'll write GP to mean the smallest closed group with property P containing G. There's been quite a lot of activity based on Tits' theorem or versions of it. So I've just listed some authors here. I don't want to spell out everything they've done, but there's various constructions. Some of them are not acting on trees anymore. Like there are examples with sort of Tits independence property fractions on buildings. Probably you could do the same for cat zero Q complexes as well, although I don't know if that's been done yet. Okay, so another motivation for what we're doing is for the structure theory of locally compact groups. We want to know about the groups that are non-discrete, compactly generated, and topologically simple. Now, in the connected case, these are all known. They're the simple Lie groups. In the totally disconnected case, though, it's much more complicated. So initially, most of the known examples of these groups were in the spirit of Lie groups. So algebraic groups over local fields, or Kac-Moody groups you can think of as kind of generalized Lie groups, or sort of modifications of these ideas. But what Tits gave us is a different way of producing simple groups. And since about 2000, these independence properties in the style of Tits have been the main source of groups in S that are not of algebraic origin, so not sort of Kac-Moody groups and so on. I have to say that it seems Tits' paper from 1970 didn't attract much attention at the time. It was published in some like collection of essays in honor of somebody or other, and yeah, it didn't seem to attract much attention at the time it was published. But in 2000, Mark Berger and Shahar Moses rediscovered Tits' work and used it to produce a whole new class of not just simple groups, but also they used it to produce lots more examples of irreducible lattices in products of trees, and that was actually their main motivation. I think they may have produced some finitely presented simple groups in that context. I can't remember. Anyway, for our purposes, the important thing is these Berger-Moses groups. So So if we write TD for the regular tree, in which each vertex has some finite number D.
Can I just ask you one thing?
Yep.
Berger-Moses, they are trying to prove to establish some rigidity results, no? Was it like they are in the continuation of Margulis or something like that, or?
I think there were, yeah, I'm not sure. There were various motivations for them to study lattices in twin trees. I can't remember exactly which one was their main motivation, but yeah, there's sort of there's two papers by them. One is about lattices, and the other one is about these universal groups.
Okay.
But
I thought I heard it together with stuff of Zimmer and things like that. Yeah.
Yeah. I'm not sure if it's exactly connected with the sort of rigidity in higher rank arithmetic lattices, because I think tree lattices are a bit different. But yeah, they certainly wanted to produce interesting examples of lattices.
Okay.
Yeah. So if you start with the regular locally finite tree, and then a permutation group on D letters, then there's a group U of F, which they call the universal group, or we can call it a Berger-Moses group, which has the following properties. So U of F has property P. It's vertex transitive. At every vertex, it has local action F. And for every edge, you can flip that edge. There's some element of U of F that sends A to the reverse of A. And second, if you have any subgroup of Aut TD, and H is vertex transitive, has local action F, and then either F is transitive or H inverts every edge, then the P closure of H is a conjugate of this U of F. So I've sort of specified U of F up to conjugacy here, because, well, I mean, there's clearly choices to be made in terms of how you match up the D neighbours of each vertex across the whole tree. But the point is that up to conjugacy in Aut TD, this is uniquely specified. And that's why it's called the universal group, because it's the sort of biggest group that has that is vertex transitive with local action F, and yeah, contains these edge inversions. Berger-Moses also proved some strong properties of groups acting on graphs where the local action is quasi-primitive, meaning that every non-trivial normal subgroup is transitive. And what they more or less proved in this context is that as long as the group is big enough, it involves these groups in the class S I mentioned before. So you get these big simple groups appearing. Yeah, they certainly proved that for groups acting on trees, but I think they had results for groups acting on general graphs as well. Okay, so more recently, Simon Smith generalized this construction to consider groups acting on trees, which are not necessarily locally finite, and in his construction, you have two orbits of vertices, so corresponding to the natural bipartition of the tree. And if the local actions are primitive but not regular, the resulting group acts primitively on each class of vertices. To explain what primitive is, basically, if you have a permutation group, one of the natural ways to break it down is to find a system of imprimitivity, which is sort of an equivalence relation on the set it's acting on that's preserved by the action. And a primitive permutation group is one that doesn't preserve any non-trivial system of imprimitivity. It doesn't preserve any non-trivial equivalence relation. So an important thing in the theory of permutation groups is to understand the structure of primitive permutation groups and their relationship to sort of general permutation groups. And this is a new construction of primitive permutation groups. So the input is sort of, I mean, it starts with primitive groups and it makes more primitive groups. But that's sort of the nature of these constructions. So Simon's also used this to obtain an Onan-Scott type theorem for infinite primitive permutation groups of finite subdegree. Which I think is in a 2019 preprint. So the Onan-Scott theorem is for finite primitive permutation groups, but Simon has managed to sort of extend it to finite subdegree. And one of the sort of key steps in this construction is this what he calls a box product, which is basically coming from this action on a tree. And it sort of like plays an equivalent role to, or it plays a complementary role to the wreath product in primitive action in the Onan-Scott theorem. So you still have the wreath product in primitive action, but you also have this box product. Okay, so what's our motivation? So we've got all these groups acting on trees with property P, or if you like, groups specified by their local actions acting on trees. And we want to put them all into a single sort of framework without making any assumptions about how the group acts on the tree other than property P. So it's sort of like a local actions version of Serre theory. And then we want to relate global properties of the group acting on the tree to the local actions description. Yeah, and we can have any size tree, any number of orbits on vertices and edges. We don't make any assumptions there. Okay, so let's say we've got a group acting on a tree. How do we record the local action structure in an efficient way? So first step is the same as Serre. We form the quotient graph of the action. So the vertices are, each vertex is an orbit of vertices on the tree. Each arc of gamma is an orbit of arcs on the tree. And then the origin and terminus maps and the reverse map are defined in the obvious way. So this map, that should be, sorry, T goes to gamma. The quotient map from T to gamma is locally surjective. So if you take a vertex in gamma and then take one vertex in its pre-image, the arcs coming out of that vertex in the pre-image will give you all the arcs of the vertex of gamma. Yeah, so I said locally surjective here, not locally bijective. So this is not it's not the universal covering tree in general, but it is locally surjective. And given a vertex of the tree, if we map it to gamma and then take the arcs, we take all the arcs that come out of the vertex of gamma, then we get one for each GV orbit. So this map here is going to be locally bijective, essentially, if and only if the local action is trivial. So in gamma, the arcs coming out of a vertex correspond to the orbits of that vertex stabilizer in the original tree. And again, this is the same as the Serre setup. So one difference here between us and Serre is we don't assume that G acts without edge inversions. And the consequence of this is that you can have loops in gamma where the loop is actually equal to its own reverse. That corresponds exactly to the case where in the original tree, you could flip the edge. So that's why we allow that, and sort of Serre doesn't. And okay, so for each vertex of gamma, if we choose some reference vertex in the tree that's in the pre-image of W, then we can take the set of arcs going into V, sorry, coming out of V, and call that XW. And then we've got G brackets W is going to be the permutation group that the vertex stabilizer induces on those arcs. So this is the local action of G at V. And then XW is partitioned into orbits of this group, which, as we've said, correspond to the elements, to correspond to the arcs coming out of W. So for each arc coming out of W, we have that should be a GW orbit, which we call X sub A, and this is the arcs coming out of A. Sorry, the arcs coming out of V, they get mapped to A. The choice of the reference vertex doesn't really affect what permutation group we get here, or the correspondence between the GW orbits and the arcs. So what we end up with is the following data. So a local action diagram consists of a connected graph gamma. For each arc of gamma, a non-empty set XA, which we call the color set of A. And then for each vertex of gamma, we have a subgroup of the permutation of the symmetric group on XV, where XV is the disjoint union of all the XAs for the arcs coming out of V. And moreover, the action of GV should be such that its orbits are exactly these sets XA. Okay, so this is the data we end up with when we try to describe the local actions of a group acting on a tree. And then there's an obvious notion of conjugacy. So you can say two groups acting on graphs are conjugate if there's a group isomorphism between the two groups, graph isomorphism between the graphs that maps one group to the other in the obvious way. And similarly, you can define isomorphisms of local action diagrams. I don't want to spell out all the details, but you can guess what the definition will be. Okay, so this is really the central idea of our theory. So it's the local action diagram, and this is our sort of version of a graph of groups. And the main theorem is that this tells you everything, and all possible local action diagrams occur. So there is a one-to-one correspondence between P-closed actions on trees up to conjugacy and local action diagrams up to isomorphism. So if you take two actions on trees, then their P-closures are conjugate if and only if their local action diagrams are isomorphic. So the local action diagram tells you exactly what the local action, so it tells you exactly what the P-closure of the original action is. And second, if you just write down any local action diagram satisfying the conditions I specified, there will be a group with that local action diagram, which we call U of delta. So we sort of have the Berger-Moses universal groups, but for all of these local action diagrams. And by construction, it will have property P. Okay, so the tricky part of the proof is, well, the more difficult part of the proof is part 2. So if you start with the local action diagram, you want to build this group U delta, and basically what you do is you take you can build a tree equipped with the quotient map to gamma with the right number of sort of neighbours of the right sort of number of arcs going into each vertex and so on. And then a colouring of that tree, which sort of specifies how the colour sets work. So, so for each arc of the tree, you give it a colour, and the colour should land in. So the colour of A is going to be in this set X of pi A, so the appropriate colour set. But then the second condition is the important one. So if you have a vertex of T, then the colours of the arcs coming out of that vertex will correspond to the colour set of the vertex in the local action diagram. And it's important here that we colour arcs. So the colour of an arc going one way doesn't tell you anything about the colour of the reverse of it. And then we define U of delta to be the group of the set of all automorphisms of the tree that act on this colouring with respect to this colouring as the specified local action. So if you take a vertex of the so if you start at a vertex of the tree, then you have a bijection from the arcs coming out of it to the color set. So I think maybe I put the inverse the wrong way around there. No, that's the right way around. So if I start with an element in the color set, I apply LV inverse, and that gives me an arc in the tree. Then I apply my automorphism of the tree, gives me another arc in the tree. And then I apply L of GV, which gets me back to the color set. Right. So that defines a permutation of the colors. And I want that permutation to be in this group. Okay, so I've drawn an example here to show how the coloring works. So on the left here is a local action diagram. The colors of the vertices here are not part of the local action diagram. I've just drawn them to show how the sort of lift to the tree works. So if we look at a white vertex in the tree here, we're meant to have local action symmetric group on 3 letters. And we have a color set RGB here. So we should have the colors red, green, and blue coming out of that vertex. And if we look at a black vertex, so the local action here is that you can flip CM, but you have to fix Y. And then we've got 2 arcs coming out. One of them is CM, and this arc is equal to its own reverse. So we've got an arc labeled CM and an arc labeled Y. What that means is that at any black vertex, you'll have a yellow arc going to a white vertex, and then cyan and magenta arcs going to black vertices. And at each vertex, each black vertex, we're going to have exactly 1 yellow, 1 cyan, and 1 magenta. So I've drawn an example here of how the coloring works. So the point is that the colors of the in arcs at a vertex could be anything. We don't keep track of those, but the colors of the arcs coming out of a vertex should be in 1-to-1 correspondence with the color set in the local action diagram. So this vertex here, we have yellow, magenta, cyan. Here we have yellow, magenta, cyan, and so on. And the point is you can always do this. You can always color the tree so that this is satisfied. And the colorings, there's some arbitrary choices to be made in the colorings, but it doesn't actually affect what the final group is. You always get the same group up to conjugacy. Okay, so that's our main construction. So I'll finish with some applications. So if you have a finite local action diagram, then that sort of encodes the situation where you have an action on a locally finite tree with property P, and there's finitely many orbits of vertices. So in principle, we've given a parameterization of these groups up to conjugacy. And if you have a vertex transitive action on a tree, then the local action diagram only has one vertex. So every edge is a loop. And then the only interesting question is whether the loop is its own reverse or not. So you have this edge reversal map on loops. And that means that there's a correspondence between vertex transitive P-closed actions on trees and pairs HR, where H is a permutation group of the appropriate degree, and R is some bijection on the orbits of H. That if you do it twice, you get back to the identity. So if you take R to be just the trivial permutation, this is the Berger-Moses group. So in the Berger-Moses one, the local action diagram is such that every edge is its own reverse because every edge can be flipped. Stéphane Tournier wrote a GAP program to sort of enumerate these things, which got to degree 11 before it got too slow. So you get some number of groups of these sizes. So for instance, there's about 20,000 conjugacy classes of P-closed vertex transitive subgroups of T11. And for comparison, the number of Berger-Moses groups of that degree is about 3,000. That's the number of permutation groups on 11 points. It's a little over 3,000. So you can see there's more of them, but for these small numbers, it's not sort of drastically more. We don't know what the sort of asymptotics of this sequence would be. I should say that the number of permutation groups has only been calculated up to about degree 18. So we probably couldn't continue this too much further anyway, just based on what's known about permutation groups. Okay, so in terms of producing examples of simple groups, we've got various results saying whether or not U of delta is compactly generated, whether or not it's discrete, whether or not it's simple. And I just gave a sufficient condition here. So if you have a local action diagram such that the graph is a tree with at least two vertices, each of the GVs is a TDLC group with compact point stabilizers, and it's generated by finitely many point stabilizers. So it's compactly generated and generated by point stabilizers. And we make sure that we don't have any trivial GVs on the leaves of gamma. Yeah, I should have said I want gamma to be a finite tree. Then the conclusion is that U delta is in this class S. It's a compactly generated non-discrete simple group. And here's an example of a group in S, which I don't think is in the literature. So you can check this satisfies all these properties. Now, what have I done here? Well, if we go back to this picture, this local action diagram does not describe a group in S because it's not a tree. So what I've done is I've unfolded it by sort of, I've sort of taken the universal cover, the sort of, universal cover of this graph, I guess, or yeah. So actually this group here is a subgroup of the previous one I drew of index 2, and it's the plus group of the previous one. So you can often do this. Yeah, so we have a sort of general recipe for producing groups, simple groups acting on trees, and we can characterize which of these are simple. Okay, and just for a final example, of an application in graph theory. So if you have a connected simple graph, gamma, we say it's two connected if it remains connected after removing any one vertex. And then a lobe of the graph is a maximal two connected subgraph. The description of the automorphism groups of the vertex transitive connected graphs that are not two connected was given a while ago. And what the idea is that you have an associated tree with vertices V gamma and L, where L is the set of lobes and V gamma is the set of vertices of the original graph. And you draw an edge between a vertex and a lobe if the vertex lives in that lobe. And the group or gamma then acts on the tree. And in our language, this is a p-closed action, so it's described by a local action diagram. The underlying graph, so you have one vertex for because it's vertex transitive, you have one vertex of the local action diagram for the vertex, the vertices of the original graph, and then you have some vertices coming off it for the lobes. So you have like a star picture, and the local action at a lobe vertex is the automorphism group of that because it acts on the vertices of the lobe, and the local action at the central vertex representing the vertices is just a bunch of symmetric groups that permute the sort of isomorphism types of lobes that live at that vertex. So I've just drawn a picture here. So on the left, you imagine this picture goes on forever. This is an example of a vertex transitive graph that's not two connected, but is connected. And then I've highlighted a lobe in red, this graph here. So the local action of the lobe is going to have two orbits of size 2, because you can sort of flip these two and flip these two. And if we look at a vertex, there are two kinds of lobe, because there's the one which has sort of 3 edges. There's one kind of lobe that has 3 edges at that vertex, and then there are 2 lobes that have 2 edges at that vertex. So the local action here is going to be cyclic group of order 2 acting on 3 points. And so we have one edge coming out here that has label A, and that represents the local action at this vertex on this lobe because it fixes it. And then you can swap these 2 lobes, so you have a local action there where you have 2 points. Okay, so yeah, the main reference at the moment is this archive preprint, which you can see there. Thanks for your attention.
All right, well, thank you very much, Colin, for this very nice talk. Yeah, very interesting. Do you have any questions for Colin? I have some, but if someone wants to go before me, I'm happy. So.
Maybe I'll just ask you, it might be a silly question, but so I guess one of the things you're interested in is coming up with interesting examples of groups with, simple properties and things like that. And you do that by looking at groups acting on trees. But, when I think of trees, I think of them as sort of like simplicial complexes, just one-dimensional. Do people study a lot like groups acting on, other simplicial complexes, and how does the theory play out there, or is there a reason why you only really look at the one-dimensional sort of case?
Yes. So the reason we look at the one-dimensional case, I guess, is that trees are easier. That's the only real reason. So there has been some work on these kind of ideas for building, and I think for cat-0 complexes. And again, it's because those have a sort of special geometry that you can exploit to talk about these things. So I don't know if the full sort of local action diagram type setup, I don't think that's known for buildings or Cat0Q complexes. I think the point here is that there's sort of no compatibility conditions between the groups. We can just pick anything. And that really is exploiting the fact that we're acting on a tree, that it's simply connected. And there's no sort of, there's no circuits of any kind. Makes things easier. Whereas as soon as you have any more structure to it, you would have to start taking into account which actions are compatible with which actions. Yeah, I should say, even in the case of groups acting on buildings, people tend to consider, for instance, right-angle buildings. So they're already kind of tree-like in a certain way.
Okay.
Yeah.
Okay, maybe two similar questions than Daniel, but not about the dimension, but about the length.
Mm-hmm.
So here you have this property IP1 that basically all you want to know is how you act on the sphere of radius 1 in your tree, in your graph, or in your tree. Of course, one would like to know what's going on the sphere of radius 2, radius 3. So can you do something like that? Or does that make sense? Is it not too complicated?
Yeah, it does make sense. So Banks Elder Willis actually that was their main motivation, to consider sort of the K local action on a tree. And you can define these groups sort of UK of F, like the Berger-Moses groups. This is something Stefan Tournier has done. Again, it gets more complicated because you have compatibility conditions. You can't choose, if you choose two neighboring vertices, you can't choose their local actions independently of each other if you go to sort of large radius, because they've got to agree on the overlap. I think in principle there should be a local action diagrams theory of K local actions, but it'll be much more complicated because you have to sort of have these. I mean, if you think in sort of the manifold language, we're sort of talking about like building sort of the group out of these local pieces, but the local pieces would start overlapping in more complicated ways if you have a K local action. So this is a big thing that Stefan wants to work on in his DECRA project, actually, is doing this kind of thing for K local actions.
I see, but the recipe to come back to produce this nice simple group that are compactly generated, it's going to be, the picture will be much more difficult. Yeah. And you already have many groups. Yeah.
The simplicity criterion itself isn't actually too different.
Okay.
The difficult part is constructing the group in the first place. Yeah.
Yeah, the input data is not the same at all. Yeah. And so what kind of other group were known? So you said basically if you take like some algebraic group over local field and things like that, this was the principal source of locally compact, totally disconnected with nice, I mean, locally compact, totally disconnected, I guess. Yeah, right.
Yeah, for producing compactly generated simple groups. Yeah.
Some PS7 or something.
Yeah. Yeah. What did I say? Yeah. So yeah, exactly. Yeah, SLN and so on. And likewise for Kac-Moody groups. Actually, the locally compact Kac-Moody groups are over finite fields. So you have to take a certain completion to get a non-discrete group. But yeah, I guess I've cheated a bit here. Another big source of examples are these groups of topological full groups.
Oh, okay.
The sort of non-discrete analogs of Higman-Thompson groups and so on. But in practice, most of the constructions we have of those, in fact, basically all the constructions we have of those are acting as almost automorphisms of trees. and the sort of the underlying tree structure has still got this independence property. So even those examples are effectively building on this sort of independence property to produce a non-discrete locally compact group.
Almost automorphism group. Okay, that will be.
Yeah, so like Neritin's group, for instance.
Yeah. Oh yeah, it's Le Boudec, right? Who's doing stuff like that? Yeah, Adrien.
Yeah, he made some other groups which were acting on trees, but they weren't acting properly on the tree. So they sort of had they had non-compact vertex stabilizers. So they don't actually fit into our framework exactly, but again, they're still in the spirit of Tits, I would say.
Yeah. Are there any other questions for Colin? Just one thing that I'm a bit curious about. What is exactly this box product here? Because you say it's like quite similar to a Reef product,
Well, it's not exactly similar to a Reef product. It's similar to the Reef product in primitive action, in the sense that you put in a primitive group and then you get out another primitive group, kind of thing. But it's so the box product is basically you look at this action on the tree, but you only consider one orbit of vertices.
Okay.
And then if you make you can choose for sort of one of the input groups to be primitive and the other one to be transitive, and then you get a group that acts primitively on one of the sets of vertices. So it's similar to how the Reith products, if you put the right groups in, you get a primitive group out.
Okay.
But obviously it's not the same in the sense that it obviously produces very different groups, and that they're often simple, for instance.
Okay, and there's no Is that like a bit the Nekrashevich-Rover groups that are a bit like that?
I'm not familiar with those.
This is kind of generalization of Thomson, when you have the Thomson act on beginning of finite paths of trees, like it will permute, right? And then you add a self-similar group that acts on the infinite, kind of the end of the path, yeah. So it's something that also Hugues look at with some specific like self-similar group, yeah. I say that because they have very interesting properties, and many of them have the high group property. Many of them act nicely on cat0 cubical complex. So I was wondering if you had something similar. Yeah.
I don't know. I mean, I'd guess that in the end they're almost automorphism groups of trees again, or that they're acting on trees by almost automorphisms.
Yeah, sorry, you're absolutely right. Yeah, the Nekrashevich-Rover actually they will be almost automorphism group of trees. That's right. Yeah.
It's funny you mentioned the Hargroup property. So been thinking about in the context of another project with Alejandro Garrido and Dave Robertson, and we came up with this family of partially ordered sets whose almost automorphism groups are, you get like a simple derived group, and it has property PW, so it has the Hargroup property. So it sort of generalizes what's known about Neritin's group there. Unfortunately, we couldn't think of how to actually construct examples of these sets that are not already basically trees. So it's this difficulty of getting away from the tree case.
You had like a post set and you look at the simplicial complex associated to it, or is it,
the simplicial complex to get property PW we came up with is a bit ad hoc. It's not particularly nice. It just proves that it has PW.
You need like to have the right example that is different from what is done. Okay.
Exactly, because we know we can apply this to like Valtraud-Lederler's examples and so on, but we want to find new examples.
Quite nice. And PW, I think is should be strictly stronger than higher group, right? In principle. It is not known if it is stronger.
I think that's right.
I think it's not known, but it should be. Yeah, right.
Yeah.
That's what it is. Yeah.
Yeah.
Okay. It's about this. It's an action of the cat zero that is slightly better than just being free and yeah. Okay. And yeah, I don't know what the situation about this question is today. If someone found an example in between, or yeah.
No, I don't know.
Okay. Yeah, I haven't seen. Yeah. Oh, okay. Yeah, I like a lot of the higher properties. This is something that I've been looking at quite a lot. Yeah, and it seems like your group. I mean, the acton trees is the
yeah. Well, actually, I don't know if Simon's groups have the high group property. So yeah, because I think I've seen the proof for like actions on locally finite trees, but the trees here are not necessarily locally finite. So I don't know.
Yeah. And the same, like for when you act on trees, often you want to look at weak amenability of calling and high group. Yeah. So it's a good Australian Danish property, so you can look at it. Yeah. Okay. All right. Well, thanks a lot for the talk again. I guess let's thanks again, Colin.
Yeah, thank you.
Very nice one. Maybe I stop the recording.